In this session, I'll discuss about the implementation of the queue data structure using an array. In our previous sessions, we have seen how a linked list can be used to internally represent a queue, and therefore I believe that this session is going to be relatively easier for you because we are going to go through the same enqueue and the dequeue methods that we discussed about the queue data structure in our previous sessions. Let us now go through the objective for today's class. Firstly, we'll discuss about how we can use arrays to implement queues. Then we'll go through the enqueue and the dequeue operations. We'll take up an example to ensure that we imbibe the concepts well. Finally, I'll discuss about circular queues and its enqueue and dequeue methods. So that's the objective for today's class. Let's just get started. Consider the sample queue that I have implemented using an array. Here the size of the array is 5, and this is evident from the fact that the indices go from 0 to 4, whereas the size of the queue is 3 because we have only 3 entries in this array which is being used to internally represent our queue data structure. Now one question that may come up in your mind is that at which end you should be adding element and at which end you should be removing elements. So suppose the client of a code invokes the method enqueue with the argument 5. That is, he wants to add a new item 5 into the queue. So should you be adding 5 at this position, or you should be creating space for 5 at this position? Now let us consider what happens if the dequeue method is called. So suppose the client invokes the dequeue method. So should the dequeue method be returning 7 or it should be returning 4? Now, just like our previous sessions where we had analyzed that at which end adding and removing elements will be beneficial, we will again analyze whether it is beneficial to add at the rear end or add at the front end, and to remove at the rear end or to remove at the front end. That we'll do next. Now let us analyze the enqueue method. Suppose we decide that we will be adding items at the front end of our queue. So when the client invokes the enqueue method with some argument, our first job is to create space for the new item. So let us take this example. I have a queue that has 3 entries, 4, 6 and 7, and the enqueue method is invoked with an argument 5. So first I need to create space, and to create space what I'll do is I'll simply shift all the items that are in the queue one place to the right, so that 7 goes over this slot, 6 will go in place of 7 and 4 will override 6. So the updated queue will be something like this. I have 4 here, 6 over here and 7 over here. And now that the space has been created, I can insert the new item. Now on face of this algorithm, it is a linear time algorithm with a complexity of big O of n. Now let us see what happens when the client of a code invokes the enqueue method, and we decide that every time enqueue method is invoked, we will be adding items at the end of a queue, that is at the rear end of the queue. So suppose the client invokes the enqueue method again with the value 5, then all I need to do is I need to simply increment the rear pointer, which is actually an index value. I'll just increment the rear index so that it will point to the next free slot. So by incrementing, rear is now holding index number 3, and then I can simply insert the new item, that is 5. And clearly this takes constant time, so its complexity is big O of 1. Let us now analyze the dequeue method and see that should we be dequeuing elements from the front end or from the rear end. Let us now analyze the dequeue method. So suppose the client invokes the dequeue method and we decide that every time dequeue is invoked, we will be removing items from the front end. So if I remove item from the front end, then I will simply return this value, and by doing so, a space will be created. Now, traditionally what happens when we delete items from the front end of an array, we shift values that is in its right slot. So traditionally we would have been shifting 6 over this slot and overriding 6 by 7, such that the updated array would be something like this, right? So again, this seems to be having a complexity of big O of n. This is a linear time algorithm. Just keep that in mind that this is a traditional way. We will come back to this once I'm done with this other option of dequeuing from the end. Now, if I decide to dequeue from the end, all I need to do is return this value that is at the rear end. I'll just return this value. So once this value has been returned, I can decrement the rear variable so that it points to the next item that is to the left of the item that has been dequeued. So rear will point over here, right? This will no longer exist. And again, this is constant time. So this has a complexity of big O of 1. So now that we have analyzed the enqueue and the dequeue method, let us now summarize what we have studied in form of a table. As you can see in this table, clearly when we try to enqueue at the start of the array, the complexity is big O of n, that is, this is a linear time algorithm. Whereas if I try to enqueue at the end, we have this operation can be done in constant time. So its complexity is big O of 1. And remember, we are always striving for constant time complexity as of now, right? Now, when we come to dequeue method, it's exactly the same. When we dequeue from the start, it has a complexity of order of n because we need to shift elements to the left. And when we dequeue from the end, we have a constant time algorithm. Now remember what I said. Traditionally, if I have an array, and suppose this array has 3 entries, 3, 4, and 5, right? And its indices are 1, 2, and 3. Traditionally, in an array, when you delete an item from the start of the array, you shift the items that are to the right of it, one place to the left. And that's why when I dequeued, my complexity turned out to be big O of n. But as you may have realized that while implementing queue, you need to work at two ends. And from here, what we can observe is that if we enqueue from the end and dequeue from the end, then only we can achieve constant time algorithm. But that's not possible. You need to work at two ends. You need two ends. So what I'm going to do is that I'll always enqueue from the rear end or from the end of the array, and I'll always dequeue from the start. Now you may say that why I'm dequeuing from the start? This has a complexity of big O of n. So I will not be following this traditional way of deleting items as I did when we studied array. What I'm going to do is every time I dequeue, I'm not going to shift items to the left. That is, suppose this is my array which is being used for representing my queue, and it has 5 slots. It has a capacity of 5 items, and so these are the indices 1, 2, 3, and 4. And at present, it has 3 entries 3, 4, and 5. This is my front end, and this is my rear end. So when the dequeue method is invoked, I'll simply return the value 3. I'll increment the front pointer, and I'll forget about the slot. So you may say that we are wasting space by forgetting about this slot. Yes, you are right. And when I discuss circular queues, you will understand that why we study circular queues in the first place. So as of now, for normal queue, when I dequeue, I'll not follow the traditional approach of shifting items to the left to fill up the gap. I'll simply increment my front pointer, that is basically an index in this case, so that the complexity of algorithm is no longer order of n or big O of n, it is now big O of 1. So from here we can clearly understand that if I use an array to implement a queue data structure, I'll be always enqueuing at the end and dequeuing at the start of the array. This is exactly the same what we have studied in linked list, and you may say that why I repeated this topic. Because I didn't repeat the topic, I just wanted you to know that why in the first place I'll be again dequeuing from the front or the start of the array and enqueuing at the end or the rear end of the array. So now that we have seen that this combination works fine for us, this is a constant time combination, we'll now move on to the pseudocode for the enqueue and the dequeue method, which I may tell you is really easy if you understood the same pseudocode while we used the linked list. Now before we get to the pseudocode for the enqueue and the dequeue method of our queue data structure that is being implemented as an array, let us first go through a concrete example to see how the enqueue and the dequeue methods work when a queue is implemented using an array. So as you can see, I have an array that has a size of 4. So the array size, let me call it A size, is 4, and at present it has only 2 entries, so the queue size is 2. I have the front variable that is at position 0, and the rear variable is at position 1. Right. Now suppose the client invokes the method enqueue and passes the value 6. So what we need to do is, first I will increment rear such that the value of rear becomes 2, and then at index number 2 of the array I can add 6, and this is shown in the following figure. I incremented, this was my rear, I incremented rear by 1, rear is now 2, and then I can add 6. So let us now move to the dequeue method. Now when the dequeue operation is invoked, I will simply return the value that is at the front end of the array, and I will then increment my front variable. So I returned 4 because 4 is at the front end, and then I will increment front. So front is now at value. So I'll increment front. So front was at 0, now front is at 1. What happens when I call in enqueue once again? I will again increment rear by 1. Rear is now 3, and then I will add 7. This is shown in the following figure. Now if I invoke dequeue method, what will happen? I will return the value in the front that is at the front of my queue. So I'll return 5 and increment front by 1, and upon doing so, front is now at index 2 and the rear variable has index 3. So this is what happens after this dequeue operation. Now suppose I again invoke the enqueue. So just like before, I'll increment rear by 1. Rear is now 4, but wait a minute. There is no index that is equivalent to 4, and therefore we cannot insert any items, because if you may have observed, we have already reached the size limit of an array, and this is a problem that exists with an array. We encountered this problem when we implemented our stacks using array, and again we have this problem. Now one more thing that we have that we observe is that the first thing is that we cannot go beyond the length of our array, and the second thing that we observe is that although there are 2 vacant slots that were created because of the dequeue operation performed in the previous steps, still we cannot insert the new items. So is there a way that I can utilize these vacant slots? So if you recall that I told you that to keep the algorithm for adding, enqueuing and removing, that is dequeuing, constant time having complexity of big O of 1, whenever I dequeue, I'll forget about the vacant slot that is created. I'll simply increment my front variable. Now at that point I told you that I will forget about these vacant slots, but now that we have encountered a problem regarding the size, we cannot perform enqueue and we have slots to perform it, but we cannot use those slots. So what I'm going to do is that a solution to this problem is that to enable our queue to wrap around. Now what does wrapping around means? Well, wrapping around means that I will, if my rear has reached the limit, the size limit of an array, and my front is at a position that is not at index 0, which means that there exist vacant slots in an array, then I will allow my rear variable to simply go to those slots. This is wrapping around, and basically wrapping around is nothing but it is circular queue. And now that you have understood how we are going to utilize these vacant spaces, we next move on to circular queues. Once we are through with circular queues, I will discuss the pseudocode for Enqueue Dequeue methods for both the normal queues as well as the circular queues in the later part of the video. So let's just get to circular queues. Now, if you recall the previous example, we were stuck at this point where the client tried to perform the enqueue operation with an item, say 9, and when we tried to increment the rear variable so that I can create space for the new item, we actually exceeded the size of the array. And at that point I told you that although we have vacant slots in the initial part of an array, but still we cannot use them. So one solution was to wrapping around the queue, or allowing the queue or the array to be circular. It simply means that letting the rear variable assume the index values of those vacant positions, right? So how can rear assume the values of these vacant positions? And to achieve this wrapping around, we'll be using our old friend modular arithmetic. So now, in our previous case, what we did was every time I needed to add something, I just incremented rear by 1 and then I added that element. Now, because we are allowing the queue to wrap around, what I'll do is every time I want to enqueue, I will increment rear by 1 as we did in previous case, but I will take this value modulo size of my array, and this will ensure that I always remain within the limits of my array. So if I'm at 3, the value of rear is 3 and the enqueue method is now invoked, I will simply increment 3 by 1, so 3 becomes 4. I will then take 4 modulo the size. Now the size of the array is 4, so 4 modulo 4 is actually 0. So the new value of the rear variable is 0. So rear is now at this position and rear is no longer at this position. So now that rear is at 0, which is vacant, so remember it has to be vacant as well. So because rear is at 0, which is vacant, I can very well insert the value 9. Now one thing you should be clear is that arrays are always linear, right? Because we are saying that we are making the array circular or we have a circular queue, it does not mean that in the computer memory the array becomes circular. It's still linear. We are just manipulating these front and the rear variables by letting rear variables assume those index values that are less than that of front, or letting the rear variable assume the values of the vacant slots that were created by the dequeue operation. We are basically wrapping around, and this is what circular queue is all about. Now there's still one point that we are missing on, and that I'll be discussing next. Now let us just continue with our example. So now I am allowing my queue or my array to be circular, right? My rear variable is at index 0, my front variable is at index 2, and obviously if the value of the rear is less than front, it means that we are in a circular queue. Now suppose the client invokes the enqueue operation with an item 8. So what I'll do is I'll increment rear by 1 modulo size of the array. So the value of rear as of now is 0. I'll increment it by 1, so this expression evaluates to 1 modulo size of the array. Size of the array is 4, so 1 modulo 4 is 1. So what I do is I will just add, now that I have a new rear value, I'll add this item to this position number 1. Now say the client again invokes the enqueue method with another argument 10. So I'll perform the same operation, rear plus 1 modulo a size, that is 1 plus 1 modulo 4, and this comes out to be 2. So according to our logic, now I should be making the rear point, or making the rear hold value 2 and replacing 6 with 10. Now that's the problem. We cannot override existing values. So therefore, from now on, we will use these two variables in our program as well. What we'll do is that we can create a helper method is full, and this method will simply return the result of comparing the array size and the queue size, and if the sizes are equal, we cannot enqueue, right? Now, because we are using array, we have this problem of getting the array full, and therefore not able to perform enqueue. This was not a problem in linked list, because in that we can get memory on demand from the operating system and basically increase the number of nodes. Now, one more thing that you should remember is that because we cannot enqueue, it is not a problem of a queue, it's actually the problem of an array. Queue does not have any size. Arrays have size, especially when they are statically declared. So now that we have seen how circular queues can be implemented by making our arrays circular with the help of our friend modular arithmetic, we can now just move on to the pseudocode for normal queues as well as circular queues that are being implemented using arrays. Now that we have seen how circular queues and normal queues are implemented using arrays, let us now just walk through the C++ code for the enqueue and the dequeue methods. In the enqueue method, first we will check whether the queue is empty, whether the queue is full or not. Only when the queue is not full, we will be able to enqueue a new item. So this is the enqueue method for our normal queue. In the first step, I will simply increment my rear variable. Then I will simply insert the item that was passed by the client into the new position of the rear, and then I can increment the size of the queue. Now this isFull method, the implementation of the isFull method is shown over here. This is a helper method that will return a boolean value which will be true if the size of the queue is equal to the size of the array, and it will be false if the size of the queue is not equal to the size of the array. Now, the implementation of the enqueue method for the circular queue is very easy. Everything is just same. All you need to do is that we need to put this modular operator over here and write array size. So if you have followed up with the examples, you can easily understand what this code does. And now we will see the C++ code for the dequeue method as well. Let's now go through the dequeue method. So first I'll check whether the queue is empty or not. If in case it is not empty, that is there are items, then we can dequeue item from the front of the array. So in the first step, I have created this local variable x in which I am storing the value that is at the front location of the array. And once I am through with that, I can then increment my front variable. Then I will decrease the size and return this local variable. But if in case our queue is empty, that is there are no items, then obviously there is no point of dequeuing when there is nothing in the queue. So I'll simply return 0. So basically the isEmpty method is again discussed over here. It is a boolean, it returns a boolean value and it will return true if the size of the queue is equals to 0, and it will return false if the size of the queue is greater than 0. So this was the implementation of the dequeue method for the normal queues. What happens if I want to perform dequeue in case of circular queues? So again, all you need to do is simply put this modular operator and write over here array size, and that is self-explanatory. So that was all about implementation of queues using array. I would now recommend you to go to your laptops or PCs and run these programs and see that if you actually understood the concepts. If you still have any problem, you may leave your questions in the comment section below. In the following lectures, I will discuss about the uses of queues. Till then, I'll say goodbye to you. Class dismissed.